Thank you. Great.
Yep.
Sorry about. Okay, great. Thank you. So the figure left shows the pie chart, the distribution of cost in a typical radar. And what's clear is that something like half of that cost is in the phased array portion of it. And it's a significant cost to go after to see about how to reduce the overall cost of the system. And if you break that out on the right and look a little more closely at how much a phased array is to the differences of it, about half of the phased array cost is in the modules themselves. And actually, interestingly enough, in all the boards and the cabling, which are high materials costs. So the reason that is, if you go to the next slide, if you take a look at any one of the arrays that you've seen over the past slides, you look on the left-hand side, is very typical geometry for that, and what I call a slat architecture. In this case, the Z-axis is used to take advantage of a lot of space, to put components and have area for cooling and so forth. The problem with that is that it also introduces a very high material cost for the boards, and the presence of many connectors and cables adds to the overall cost in a surprisingly high way. Another way that the cost gets driven here is in the modules and the way that we currently tend to package them. I'll talk a little more detail on the next slide about that. On the right-hand side is something that's a little more typical of what we see in the wireless cell phone industry approach of trying to integrate as much as possible into printed circuit boards or on chip. By doing that, you can significantly reduce cost. And as I say, there are several ways you do that. First, by reducing the board area. In this case, the example I'm showing is an S-band of over a factor of 6 board area reduction. And then the cost of these connectors and actually the labor that it takes to normally to put connectors and cables together is another big advantage with an integrated beamforming system. And finally, the way that chips are being packaged now in most of our wireless systems and cell phones is in the so-called quad flat no lead or plastic chip packages. And these are standardized and they're easy to use in automated pick and place. And therefore, I think that what we're seeing now is that use of them in arrays is becoming much more widespread. And the difference being now, instead of holding the environment and hermeticity at the TR module level, we're actually controlling it at the tile or array levels. So the line replaceable unit is now sort of a building block, in this case, of 64 elements rather than a single element module. So that's a major difference between those two approaches. The next slide, please. Lastly, why these things are so much more expensive. You can see on the left, this is a conventional TR module with a hermetic metal housing. The substrates, the circular, the connectors, all of these things are designed to be very robust, environmentally controlled, and hermetic. But because of that, they also have very high material and assembly costs. And on the right is an example module that has been developed over the past 5 years or so at S-band, that you can see that it has many advantages because it again uses plastic packaging, a very inexpensive substrate, and this is mounted onto a PC board using solder mounting, and that's done in an automatic pick and place. So these are kinds of things that we see as being significant cost benefits by building phased arrays. If you next slide, please. So to look at the cost comparison, I'm showing a table here that does come right out of the paper, and it has a breakout of things like the chipset cost and the module packaging, the boards, and so forth. And what you see is that the big cost benefits by going to the tile come in several major places. One, the actual packaging, as I described before, but also in the cost of the RF boards that is significantly reduced in a planar tile type of architecture. And then finally, just because the cooling is done in a sort of a two-dimensional parallel face of the array, that actually has a major reduction in the cooling apparatus as well. And so these two numbers that I'm showing you here are based on a cost model included in the appendix of the paper and the proceedings that you can go and look at and see how we distribute those, and actually you can take use of it and try it for yourself to see how it compares. But we've at least several examples of industry-based designs that match up very well with this factor of 5x between tile and slat. So if you go to the next slide, please. So just looking at this from the user's perspective, which is I need to have a certain amount of transmit power per unit area, and ultimately it's going to have a limitation on how much things cost per unit area. And I'm showing you here the slat array and the tile array. It's all normalized, but ideally you can see here you'd like to be able to take advantage of this major cost reduction. There's the two operating points here at the very low end where it's air cooled, and I think it's pretty clear that, and we are doing air cooling with tile and slat based arrays. Now I think that the major benefit will be when we can go to high power density and create liquid cooling into a tile to be able to pull away the heat. But the payoff here is very significant. It's something on the order of a factor of 5. So if you think about the overall benefit of the radar system, that's something like a 40% cost reduction of the total system. So the next slide, please. Now the area of space we're working in here to evolve phased arrays is shown kind of in this power and frequency dimensions here. There's a point in the power axes that you go beyond air cooling. There's a capability that we use in a system called MPAR, which is air cooled, and above about 3 kilowatts per meter squared, you have to go to integrated cooling of either liquid or two-phase, depending on how much higher you are. And so that's going up on the power axis. Going on the frequency axis, now the challenge is to integrate things on a much smaller lattice. A KU band, for example, it's a 1 centimeter lattice. So you have to fit the module, the cooling, and the power management interfacing. All that has to fit in the lattice, and that becomes an integration challenge. In the upper right, you have certainly both of those two challenges merged together to be able to have not only a very high power density and liquid cooling to get the heat out, but you've also got a large number of chips. And so, in my view, I think single chip solutions are going to be imperative to be able to not only to fit into the lattice, but also to make those affordable. The number of modules per unit area at the higher frequencies will drive the cost of the overall aperture. So the next slide, please. I'll just summarize. The thought here is that the typical packaging approaches, I think, have been done maybe because they're relatively small volume and very high performance. And what we're looking to do here is to use commercial practice and to take advantage of assembly and test procedures and other packaging approaches. Tile-based approach is a very interesting and capable way of doing that, and we're demonstrating that at mod power levels and lower frequencies. And I think the interesting challenge for the phased array engineers going forward is to migrate those things into higher frequencies and higher power densities. And that I think things like integrated two-dimensional cooling and a highly integrated system on chip will be the path forward. Thank you.